So basically, this is both of your first classes with me. So real quick, as far as the setup we have here, there's obviously a camera for myself if you, for whatever reason, want to watch me talk. But ideally, you would be having a look at the screen share, which you can find at the top of your Zoom window. That'll just toggle between whether you're looking at a screen share or the people in the meeting. And the other thing would be the camera that I use for any handwritten notes. So ideally what you probably do is pin that tab. That'll be, that's essentially just like another account as a meeting participant. So if you can just find the thing that's looking at my notebook, right click that and pin it, that'll make it easier for you to sort of swap back and forth between the tabs that we'll be discussing. Any questions about that so far before I dive in? Cool. Okay. So today's agenda is a bit of a catch-up agenda. We're going to be covering the applications of quadratics, which is the thing we did in class 1 this week, and some transformation fundamentals, which is the thing we did in class 2. This is obviously your first class for both of you, so I'll go through them at the same sort of pace I would have done for the first time we had a look at it. And if there's any questions, of course, feel free to jump out and just let me know. I'm more than happy to go through things in more detail. But okay, so I will divert your attention to the screen share specifically. That's where the bulk of what I'll be talking about will be. So one of the main applications of quadratics is essentially finding the results of simultaneous equations that have to do with quadratics. A lot of the time, or at least in this particular circumstance, we're going to have a look at when linear equations intersect with quadratic equations, or at least they're related in some way. They might not intersect. In this case, they do. They intersect at a specific point. This is what's referred to as one solution to the set of simultaneous equations, simply because they only touch at a single point. The other couple of options you would have would be two solutions. So essentially your linear would cut through two separate points on the quadratic, and no solutions, which is simply that your linear doesn't touch at all. They're never going to interact with each other. Each of those is solved in a similar way. So for instance, if we work with our one solution approach, so we're trying to solve the set of simultaneous equations, a very basic example here, it's just a quadratic and a linear. There's no other coefficients in there that are unknown. We solve this the same way we solve any other simultaneous equations, which is just equate the two things together, thus you cancel out one of the variables, in this case y. What you're left with is a resulting equation which has only one variable, in this case x, and you solve that however you solve that equation. In this case, the quadratic condenses down really easily, so there's not much else to be talked about there. Everything just sort of cancels out, and you get a nice and easy x equals 0. Sub that back in to get your y equals 3 in this case. Simple enough so far? Sweet. Two solutions, again, this is sort of just showing you what's possible to happen between any linear and quadratic. We'll get into some more complicated versions of these later. Again, the exact same procedure, make them equal to each other. In this case, we get yet another quadratic because, shockingly, whenever you do addition or subtraction between a quadratic and a linear, the highest power in that sequence is still 2. So you'll still get some sort of quadratic by the end of it. This is just some other quadratic which you solve using whatever method you like to for solving quadratics. In this case, factorization is the way I went. You've got quadratic formula, you've got completing the square if you really hate yourself, because that'll take a lot longer. There's plenty of options you have available there. Get your two solutions, shove them back in to get your two y values, and you'll get your two sets of solutions there. Someone's just asked if I sent the link for the group. Who's this? I will have to forward that up later. It is too late. Okay, and the last option would be no solutions, right? So what you'll end up with is a quadratic which cannot actually be solved. So whether you do your quadratic formula or otherwise, you won't actually find any solutions, simply because your quadratic is either fully above the x-axis or fully below the x-axis. the fastest way to go about that would be to check the discriminant. So you would kind of naturally do that as you're using the quadratic formula to solve something, since it's just a term inside of the square root. If you get a negative, there will be no solutions. So those are all the fundamentals there. What's more likely to show up is, rather than be told to just solve a set of quadratic and linear, you want to figure out how many solutions are there to a set of quadratic or linear. That is a bit more challenging later on. Do I have an example of, yeah, here we go, all the way down here, where you'll essentially have additional coefficients in there, and you'll be forced to figure out, hey, what kinds of coefficients do I need to force one of these situations to happen? But we'll get there in a bit. What was it going on about here? So the main way you can determine a number of solutions ahead of time would be to use the discriminant approach. Now, it's important to know what you actually apply the discriminant to. You don't apply it to this quadratic. You apply it to the resulting quadratic after having equated the linear and the quadratic together. So we saw earlier, we would equate the linear and the quadratic, we would simplify it, and we would get another quadratic. That's the thing you want to find the discriminant of to figure out if it has no solution, one solution, or two solutions. Re-explain the process of doing the discriminant? Absolutely. So the discriminant, do I have it up here? B squared minus 4ac somewhere. Yeah, there it is. So discriminant is simply a part of the quadratic formula, which is this term here, the b squared minus 4ac. So what I'll do is I'll specifically get up my notes on just discriminant so you can see where that actually came from. One moment. Quadratic formula. So this thing here is your full quadratic formula. You've got x equals negative b plus minus that square root term, and that b squared minus 4ac, that thing there is the discriminant. It's just a keyword given to that sequence of letters. Now, the reason why it's important is because of what it implies about the results of your quadratic formula. Because it's a term inside of a square root, there are a few restrictions around what that term can be, whether it's positive or negative, will depend on basically the outcome of your quadratic formula. So for instance, if your discriminant, so the inside of the square root, is a positive number, then you're fine, right? You can always take the square root of any positive number. It might not give you a nice answer, but it will give you a valid answer. And when you look at what happens to the quadratic formula, that plus minus square root, well, you're going to have a plus and a minus version of that root. Two solutions, therefore, anytime you have your discriminant, the inside of that root, as positive, you'll always have two solutions to that quadratic. That's the first sort of scenario there. Is that making sense so far? Awesome. Okay. So the second scenario is what happens if discriminant is 0. So again, remember, it's just the square root, the inside of the square root term. Well, if the inside of the square root becomes 0, the square root itself will also become 0. So whether you add or subtract 0, you basically get the exact same outcome, right? There's no actual difference there. So your entire quadratic formula condenses down into one solution, specifically negative b over 2a, whatever that turns out to be. And so for that reason, anytime your discriminant is 0, you'll always only ever have one solution, because that plus minus becomes irrelevant. It disappears because it becomes 0. And lastly, the reason why you get no solutions for a negative discriminant is because you're never going to take the square root of a negative number. In math methods, anyway. Anyone doing spec will play with answers that will have negatives inside of the square roots. Those are referred to as imaginary numbers, or sometimes complex numbers. That's beyond the scope of this lesson. Yeah, that's beyond the scope of this lesson. We don't do specialist math stuff here. You'll see it soon enough if you are doing specialist math. Okay, cool. So that's the discriminant side of things there. Is it clear enough about that? Nice. So, having gone through that, it should now make a decent number of sense why the discriminant will tell us these scenarios, right? 2 solutions, 1 solution, no solution. This is generic for all possible quadratics, and so in that sense, it can be applied to these quadratics. Just making sure, again, you do it only after you've applied your simultaneous equations approach, where you equate the 2 equations together. This looks like a bunch of nastiness simply because it's fully generic. It'll make a lot more sense when we have nicer things to work with. This would be the nicest thing. You wouldn't necessarily need to use this approach. Again, like, it's obvious how many solutions this is going to have, but if you do apply discriminant to it, sure enough, you'll get discriminant 0, which implies there should only be 1 solution. There's just another set of examples here for whether the discriminant is negative, whether the discriminant is positive, you get the solutions you expect. It's a bit useless for these examples because you can just solve it and then know ahead of time what the number of solutions is. It's more important for these sorts of examples, which are referred to as literals, which is where you have that additional coefficient in there. Okay, so that additional coefficient, how do we work with these sorts of questions? These sorts of questions, you are trying to solve for that coefficient such that you have either 1 solution, 2 solutions, or no solution. The question will tell you which one you need to force to happen. So in this case, we're trying to force 1 solution. We'll start like we always have, which is equating the quadratic to the linear, and then getting everything onto the same side, creating some resulting quadratic on that left-hand side. My preference has always been to group the terms, so it's a lot easier to see what's my A, what's my B, what's my C, because you'll need all 3 of those terms to calculate your discriminant. So you look at this thing and you'll be like, okay, I can't solve that normally. There's too many coefficients in there to just use the quadratic formula. Not particularly pleasant. But what you'll find is if you do the discriminant, because you're only taking the coefficients off of all of these x terms, you will now only have 1 coefficient or 1 variable in your equation. So you get your discriminant from this resulting quadratic, and what you're trying to target will depend on what you set your discriminant equal to. 1 solution has always been discriminant 0, so we make it equal to 0. This is just a linear, so we just solve it like a linear. Fair enough on that one. Yeah, and at any point, if any of this is getting too confusing, feel free to interrupt me, send a text, hop off mute, however you want to go about it. 2 solutions. I believe this is the same quadratic. X squared minus x minus 12, x plus k. Yeah. So basically, I've used the same set of quadratic and linear just to show you that this set of equations doesn't matter. It's more so what you're trying to target. So again, we start exactly the same way, get our same resulting quadratic. This time, because we want 2 solutions, we want to make this thing greater than 0 rather than just equal to 0. It's inequalities, but it's also just linear, so it's not too bad to do a linear inequality. You just need to... I'm getting all sorts of messages today. My God, I'm going to put this on Do Not Disturb. You just solve this like you would for any linear inequality. And lastly, for no solutions, we know the discriminant has to be negative, in which case we are making it less than 0. And so you can see we're hitting the same number pretty much every time, obviously just because we're going either side of 0, essentially. So that's simultaneous, linear, and quadratic. It mainly shows up in your Unit 1 and 2 stuff, not so much Unit 3 and 4, but it has been known to happen. That's it for that portion. Anything else to clarify from that?
I was wondering, where can we find these worksheet explanations? Is it on the website or?
Where to find? Yeah, so these are on the school thing that you would have joined. I think you grabbed the resource pack, yeah?
Yeah.
Yeah, that's all. All of these are available there. This is specifically going to be in the functions and relations and then quadratics section there. Send me a text afterwards if you're still having trouble finding it. I'll sort that out. Yeah, okay. And the final application of quadratics is going to be the families of quadratics style questions, which is basically you have a fully generic quadratic. Sometimes you'll have a picture of a quadratic, and your goal is to figure out what's the rule of that quadratic. So these are like the rules, for example. There's three main forms that you could have. You could have the generic polynomial / quadratic form, which is just your ax squared plus bx plus c. You could have it in a factorized form, or you could have it in like your completed square form, or turning point form. Now, you'll be able to use any one of these dependent on what information you have provided to you. Technically, you can use any of them for any question, but you'll quickly realize that some are going to be a lot easier to use than others, depending on what you're provided. Like, for instance, if you have a turning point and a point, it's best that you would use the turning point form. And the reason why is because you can look at your turning point and very quickly realize, okay, well, turning point's at 1, 3. That means I should have an x minus 1 and I should have a plus 3. This minus 1 dictating a horizontal translation to the right by 1, and this plus 3 being a vertical translation of 3. Are we all familiar enough with turning point form of the quadratic? If not, just let me know. And so yeah, because we've used a turning point form, we can basically double dip on a single point. Usually when you have a point in an equation, that pretty much can only be used for solving one variable in that equation. However, in this particular circumstance, because we're using the turning point form, we can kind of double dip and get both coefficients off of that. In pretty much every case, you'll have this a coefficient left over. And again, in pretty much every case, you'll be subbing in whatever the remaining point in your equation or picture is. So in this case, it's 0, 4. Shove in 0, 4. You get your a equals 1. And depending on what the question is asked for, you might need to give the rule of the equation, which would be this. Or it might literally be asking you what's a, what's b, what's c, in which case you would literally write a equals this, b equals this, c equals this. In this case, it'd be a equals 1. B equals -1 and C equals 3. Cool enough? Okay. Another example. So in this case, we have two axes intercepts and a point. When you specifically have axis intercepts, or I guess even more specifically, the x-axis intercepts, the most effective option is going to be the factorized form of the quadratic, simply because if you remember from using your null factor law, each of the solutions of these factors, each of the solutions of these factors is the x-intercept. And so for that, if we know we have cuts at -2 and 1, we're going to have our +2 and -1 terms in there. Once again, a is left alone. We have this other point. We do the exact same thing we did before. Sub in the point, solve for a. Lastly, and the worst case scenario will be if you have 3 random points. This one is specifically like a y-intercept, but doesn't really matter too much. It is kind of nice to have a y-intercept because the way you solve this kind of scenario is with the ax squared plus bx plus c version of the polynomial, or version of the quadratic, I should say. The y-intercept is kind of nice because when you sub in your x equals 0 from this point, it will kill the a and the b term, giving you the c off rip. So that stops it from being a 3-way simultaneous equation, now back to a 2-way simultaneous equation, which is not nearly as bad. But still, I mean, kind of lengthy, right? I know I'm writing extra text to explain the steps, but that's still a fair amount of work to put in when you compare to all these other solutions, which kind of just get immediately subbed in, plug and play. So this is what you get if your teacher hates you and wants to write a particularly annoying sack. If you're lucky, you might get this in like a tech active thing instead, so you can just sort of use the CAS to simultaneous solve for you. But yeah, as far as like how we actually perform the simultaneous, in this case I've used elimination actually. So you sub in the 2 points into your ax squared plus bx plus c, simplify as much as you would like to, and in this case elimination, I saw there was a negative b here, a positive b here, So you just add the two equations together, thus cancelling out the b's. Does anyone need a recap on how elimination method works? Is that a thumbs up for yes, I should do it?
Yep.
Yeah, okay. So elimination method is where you perform one of the basic operations, usually addition or subtraction, on the full set of equations. So you can see I've labeled this one number 1, I've labeled this one number 2. This arithmetic here, saying equation 1 plus equation 2, simply means you would line up your equations sort of like vertically on top of each other and perform whatever that operation is in these sort of like vertical slices. So for instance, you've got the 5 over here and the negative 1 over here. If you're doing equation 1 plus equation 2, you do 5 plus negative 1. That's this bit here. Then you would do a plus a. That's this bit here. And then you would do negative b plus b. That's that bit there. So you essentially line up your two equations on top of each other and just add across the vertical slices. If this was subtraction, you would obviously just subtract vertically downwards. You can do multiplication and division, just not in the way I described then. Multiplication and division is more so to apply to a single equation to sort of make it able to, how to say, to get it in a stage where you can then do an addition or subtraction. Because yes, we can do these operations, but it's kind of useless if we just choose them willy-nilly. The idea is you want to look at the variables that you have and see what basic operation, addition or subtraction, could I apply to the equation that would kill one of these variables. In this case, you actually had a lot of freedom, right? There's a positive a here, a positive a here, therefore a subtraction could have worked as well, a minus a. There's a negative b here, a positive b here. That's why I specifically did the plus. So in this case, it didn't actually matter which one you did. You would just get, you would either solve the a or the b first, depending on which one you did. Clear enough on how the elimination method works? Sweet. In all cases, after you do your initial elimination, you'll then move on to substitution. This is something everyone's already familiar with. You've got one solution, you just sew it back into any of your other equations. Whether you sub it into equation 1 or equation 2 is purely up to whatever you think looks easiest to solve. And a lot of times there is actually one that's a lot easier to solve than the other. In this case, it's kind of whatever. They're both just simple enough linears. Okay, so that's the families of function style questions. That's where you have maybe a picture or maybe it's in a worded form that they give you a bunch of known information about the quadratic and they're saying, good luck, go find the rule. The last and probably most common type of application for quadratics is going to be the maximum or minimum style problems, which is simply that you want to find the maximum or minimum of a certain quantity. Typically, when it's quadratics, you're looking at like areas, that sort of thing. The reason why is because your area is calculated like length times width. That's 2 dimensions, x times x, x squared. So that's sort of the logic as to why you're typically using quadratics for this sort of thing. There's a big 4-step process here, but that's just a lot of text. We're going to have a look at how to actually apply that, and that'll be a lot easier than just trying to picture it in your head. A lot of the time you'll be finding maximums. I've very rarely seen it ever be a minimum. So this is probably the most appropriate to have a look at. And by far, this is going to be the most common, right? You're going to have some rectangle of some sort. In this case, we're told the total length of the wire that we're going to use to fence off a garden, specifically a rectangular garden. And we want to figure out how do we, well, like what would be the maximum possible area that we can enclose. These ones always have a shortcut, by the way. The maximum area is always going to be given by a square. So if you ever have a rectangular shape, just make it a square, and then whatever the area of that square is going to be the maximum. But if for whatever reason that slips your mind, or if you just want a generic approach for literally any type of shape, then this is what you'd follow. First things first, get the equation that is the basic area equation of that quantity. So in this case, we're doing a rectangle, it's length times width. Problem with this is we have technically 3 variables in there. We've got area, length, width, whereas with equations, we sort of want to have like a y and an x, right? 2 variables only. So we need to figure out how am I going to rewrite this so there's only 1 variable in there. There will always be another piece of information in the question that will allow you to rearrange for a single variable. In this case, it's the fact that we are told there is 20 meters total of fencing wire. So in other words, our perimeter is 20. So we create our perimeter equation. We have a rectangle, so it's going to be made up of 2 lengths and 2 widths. So our perimeter of 20 is going to be 2L plus 2W. These are 2 equations with, well, 2 unknowns, quote unquote. And so all we're going to do is rearrange this perimeter equation into any variable. Doesn't actually matter which one you want to use. L or W will work just as fine. In this case, I've chosen to use W. You do your rearranging, and all you're going to do is replace whatever that letter was with whatever it now equals. So that gets us from a nastier area equation into something we can actually sketch now. This is a function a of L, right? Area on the y-axis and length is now on the x-axis. Starting to see how this might be a quadratic now. If you were to expand this out, for instance, you would get a minus L squared going on. From there, probably the easiest thing to do from here is to just get a picture. That way you can sort of visualize and get a rough idea of what you would expect the area to look like. You're not really going to have much y-axis information, but at the very least you'll be able to see the overall shape of what your area is going to look like as the length changes. This should be super simple to bash out real quick. The coefficient here is going to tell you that there's a cut at 0, and this one's going to tell you a cut at 10. It's a negative quadratic. If you were to expand that out, you would get negative x squared. So it's going to be a pointing down parabola. Practically every single time you do an application, it's going to look like this. Some version of this where it cuts through 0 and cuts through some other point. Problem is with this one is that the entire quadratic is not necessarily valid. Before I explain why, does anyone know why the full quadratic might not be valid? Takes a bit of critical thinking. It is also on the page if anyone wants to read it and tell me.
Is it in because like you can't have a negative area, so that's why you don't need the rest of the graph.
Yeah, that's right. Negative area doesn't exist in the real world, so we're going to chop off that entire bottom portion of the quadratic because y values are area values in this case. Sometimes the x stuff will also matter. That'll be more so when you look at the polynomials, when you have like cubes or rectangular prisms to make. That's when some x information starts to become important to understand as well. But for this one, not so much. I mean, yes, you do want to make sure there's no negative length, but that's kind of already covered because as soon as you go negative, you've also got negative area. So we're only specifically looking at this part. From here, it's pretty easy to see where the maximum is. It's there. And if we know anything about quadratics, we know that the turning point of a quadratic will always be dead center of its x-intercepts. So we know at the very least the x-coordinate of that maximum is going to be 5. That's just a basic midpoint equation. Alternatively, you could do, what else? Axis of symmetry, if you really wanted to. You could complete the square to get your turning point form, which wouldn't be that bad of an idea because you do end up needing the y value anyway. But the fastest is still just going to be, yep, midpoint's there at 5, shove that back into your area equation, and yeah, you'll get your area that you're looking for. These are applications, so don't forget that there's a unit applied to these. That'll be evident in the question itself. Meters was used, so we would use meters squared for our unit. And just sort of to come full circle on this, what we just found was that a length of 5 would give us the maximum area. If we then go and have a look at our area equation, we knew that a length of 5 gave us 25. If we then go ahead and solve for the width, it's also going to become 5. So again, length 5, width 5, we have a square. So this will always resolve into being a square. That's a shortcut way for these, anyway. But this will be applicable to literally all the polynomials and different shapes and volumes and all sorts of other stuff, if you follow that procedure. Okay, anything to clarify before I move on to this slight nuance? Awesome. In some rarer circumstances, when there are further restrictions applied to your scenario, the maximum isn't necessarily guaranteed to be a turning point. Like, for instance, in this case, we have a restriction, which is the length of one side cannot be longer than 4 meters. I've used the exact same scenario, but just sort of tack that on so we can kind of cheat a little bit, use the exact same picture we had before. Just keep in mind that our x-axis was L, it was length. And in this case, even if you did solve for W, it doesn't matter. It's still a length of the shape. So in either case, you're still going to draw this exact same cutoff, which is the length cannot exceed 4. And so instead of taking the actual maximum, you just take whatever the y value is, the area, for a length of 4 instead. And then, yeah, just again, same as before. Shove that in, get your area value. That's it for the quadratic side of things. Yeah, any questions so far? So these lessons are normally meant to be a sort of recap on these sorts of things, which is why it's kind of lecture heavy. There's a lot of content that was covered in class 1, class 2. I am curious, should I keep going into transformations, or do we want to practice some of this quadratic stuff? Happy to do either.
I think practice would be good.
Practicing? Yeah, sure. Okay, there was a few specific things in there. The most common by far is going to be the maximum or minimum style problems. Was there anything else in there you guys want to hone in on instead? Cool. Okay, this is Unit 341. If I want just quadratics, I should probably bring up to Unit 1 and 2. Let me grab that. Okay, quadratics 3L. 126. My copy of this book, unfortunately, does not have a nice set of chapters that I can just click on, so I do have to be a bit barbaric and just scroll directly to it. Okay, cool. So this is the first kind of question, very similar to what we just had a look at. Do you guys want to attempt it yourselves and then let me know how you go, or should we do it all together for the first one?
Happy to try it.
Both okay with that? Yeah, sure. Have a crack. So that'll be 3L, and we'll make it. How far are we going to go? Yeah, sure. We'll do it all in A, B, C. So as soon as you guys get A, let me know.
Oh wait, are we doing it together or?
Oh, I thought you said you were going to do it.
Oh no, I was just wondering.
So do you want to do it together, or do you want to do it yourself?
Happy with either.
Okay, well, we'll stick to the original plan, and we'll take it from there. Sorry, Norias, did you say something?
Can we do it together?
Yeah, oh, sure, yeah, let's do it together. Okay, cool. So for this one, I will now bring up the handwritten portion, which I do on my phone, oddly enough. Okay, let me pull it. Oops, that's the wrong one. Cool. Okay, so we're told we have 60 meters of fencing wire and we want to construct a fence. So probably one of the first things you'd want to do is just sort of, get a rough picture of what this fence might look like. And you'd have your 60 meters as the amount of fencing wire that is available to you. This will focus eventually. There we go. First question is to simply, so it says write down the rule connecting A and X. That simply just means find the area equation purely in terms of X. They did also come with a bit of a picture there. They're saying that X is this thing here. So if we wanted to create a rule connecting A and X, or in other words, an area equation, just generically speaking, how do you find the area of a shape like this?
Sorry, what was the question?
Yeah, so we're trying to create our area equation. Generically speaking, how do we try to find the area of a shape like this?
Length by width.
Easy, length by width. Area is equal to length times width. Unfortunately, those are two variables, neither of which are x. So our goal is to try and do something to get the L and W out of there and purely just use x's. Any thoughts on how we might do that?
Sorry, I just missed the question again. Could you repeat, please?
Yeah. So the challenge with this area equation is that it has L and W in it. Our goal is to get it purely in terms of x. So my question was, any ideas on how we might go about achieving that?
Not sure.
Not sure. Okay. Well, there's other information in the question. Namely, we were told that there is 60 meters in total to work with. That's going to be important to use at some point.
I think in the example, I think it was like you made an equation for the perimeter,
Sure did.
and then
yeah.
that was the simultaneous equation with the one for the area.
Yeah, that's pretty much it, right? So perimeter was 60. What's
So
going to go?
2L and 2W.
Yeah, 2L, 2W. Nice. 2L plus 2W. That's a nice equation. What are we going to do with it?
And then try to simplify that.
Yep. So what's my next step going to look like?
So it would come down to 30 equals length plus width.
Yep. So that's just dividing everything by 2. Nice. Oh, well, plus width. Whoops. What else do we need to do?
I think this is where you start with the simultaneous equation.
Yeah, so I did use the term a simultaneous equation. It's not exactly a simultaneous, but we do use similar techniques, namely substitution. So you can see we have an equation here with L's and W's. We have an equation here with L's and W's. If our goal is to try and remove all the L's and W's, one technique here can allow us to do at least one of those things. What could we do?
Not sure.
Not sure. Okay. Anyone else? Any ideas? I'll give it a bit. In fact, what I'll do is I'll pull up on my screen share as well the version of this that we did, so you can see if you can apply it. Yeah, all of that should be relevant. So if you want to hop over to the screen share as well, see if you can reverse engineer what it is, what the next step should be, rather.
Yeah, rearranging so there's only one variable on each side of the equation.
Sounds pretty good to me. How are we going to do that?
Just maybe just subtracting one to the other side.
Yep, perfect. Let's say, I don't know, we'll do 30 minus W is equal to L. Cool. One of them is now over to the other side. Well, what are we going to do with this result?
I think we still have to move one of the variables for the area equation as well.
Yeah. So what's that going to look like?
That could just be area divided by width equals length.
Area divided by width equals length. You could do that, yeah. You do still want to get the area on its own.
Okay.
There's a bit of a simpler thing to get rid of another variable. And that would just be simply like looking at this picture, right? Like this length that I've labeled x, which of those variables is that going to correspond to?
Width.
Width, absolutely. So this w here is in fact just an x. So that's the simplest sort of thing to apply there. We got rid of our width. All we got to do is get rid of this length. What are we going to do?
So do we need the area by itself or the x by itself?
We need
For
the
that
area
equation.
by itself. We're trying to create an area equation. So
Okay.
whatever like the name of the equation is the thing that needs to be on its own.
Yeah, I'm not sure about this part.
Not sure. Okay. Well, we did some work over here. Let's just kind of chill in there for a bit. We've got some work over here. We're trying to fix this one up. Why did we rearrange for L?
Is this where the simultaneous equation comes in?
Basically, yeah. So it's more of a substitution specifically. So, you know, we have this thing that says L is the same thing as 30 minus W.
Yep.
Yeah.
So then the area would be equal to 30 minus W times x.
That's it. Yeah, 30 minus W times X. And there's one final thing to do. We have just put another W back in there. What are we going to do to fix that up?
I'd change it to x, I think it was.
Yeah, just changing it to X. We already knew the width was just going to be the same as X.
Yeah. Doesn't really make a difference if you change it as long as you just know that's the width or x anyways.
That's mostly true, yeah. The only thing I'll touch on there is that the textbook did say get a rule for A in terms of X. So you do want to be pretty specific with using X in this scenario anyway.
Okay.
But yeah, they are the same thing. You're right. Part B just says sketch the graph. This is still just a quadratic, so how do we sketch a quadratic like this?
Well, first, maybe just expand the brackets.
Yeah, so expanding could be fine. You do have an alternative method of solving it, but we'll have a look at that later, I suppose. So minus x squared, minus x squared plus 30x. Now we're going to sketch that. It is the tougher approach. That makes sense.
Sorry. I thought you said. Yeah, just finding the intercepts.
Yeah, finding the intercepts. How do you do that?
So just set y equal to 0.
Yep, y equals 0. So in this case, that'd be our a equals 0. 0 equals minus x squared plus 30x. What else?
The other intercept as well, if you want.
Yeah, okay, so we can set up that other equation, sure, which would look like what? We do y equals 0 for x intercept. We can either follow this path and finish that one off, or, you know, as you said, you could also set up the y intercept equation as well if you wanted to. What's next?
I mean, what I've done sometimes, like if you find the vertex, so with negative b over 2a.
Yeah, brilliant. Let's do that. So negative b over 2a x equals negative 30 over 2 times a, which is negative 1.
And then once you get the x value of the vertex, you can figure out what the axis of symmetry is.
Yes, that does become the axis of symmetry. Yeah, whatever the solution to your x equals negative b over 2a is actually the axis of symmetry. Yeah. All right,
and
cool.
then just join it from the intercepts and to the vertex.
Yep. We do need to get the intercepts though, still.
Oh, sorry, I thought we already, yeah. So 0 equals negative x squared plus 30x.
Mm-hmm.
So that was the y-intercept.
X intercept.
Oh, sorry, x-intercept. So simplify that. So you'd get x equals 0 or 30?
Yep. How did you come to that conclusion?
Sorry?
That is correct. How did you get that?
Just taking the factor out of the equation, so negative x.
Yeah. So coming back to this one essentially.
And then just once you take out the factor and then you set each one equal to 0.
That's it. Yeah. So you go back to the factorized form, you do your null factor law, that'll give you x equals 0 or 30 minus x equals 0, both of which give you the solutions you're looking for. There's the 30, there's the 0, and we know it's a negative quadratic, so we're just going to do something like this. Kind of already cheating a step just by cutting off that bottom bit. We're already familiar with the fact that area cannot be negative, so we're not going to draw any of that. So this approach worked well enough. What I will say, probably the fastest approach is going to be use this right off rip to get your x-intercepts, because you can kind of quickly see, okay, this is going to give me the term x equals 0, this is going to give me the term x equals 30, and from there what you'll always notice is that the vertex is always going to be the midpoint of those two things. So rather than do 1, 2, well, I mean, there's only 2 lines of working, but still, knowing the midpoint between 0 and 30 is kind of like that's an instant thing. Sort of speed you up a little bit. But again, this works perfectly fine as well. If you better to have a solution than no solution, right? But yeah, that'll get our graph, which was the approach for part B. Anything further to clarify about getting the graph?
Is there a faster way to do it, or is that just the method?
So yeah, that's sort of what I was explaining at the end, which is the fastest way to do it is look directly at this. That tells you x equals 0, x equals 30 immediately from the null factor law. And the x equals 15 is always just the midpoint of 0 and 30. So in my head, I go, that's 30, that's 0, middle is 15, and I can already see it's a negative quadratic. So you just go ahead and draw that. You don't need this bit here, and you don't need any this over here. You can just do it by looking at that one equation. That's obviously going to take a bit of practice though. You do need to be very familiar and comfortable with how quadratics work, but these are the quick fire things that you'll need to eventually build up to. Cool. Okay. That's sketching the graph. Final part, determine the maximum area. So remember, what we've just done is draw an area graph. We need to now determine what is the maximum possible area. How might we do that?
Because you know that 15 is the x coordinate for the vertex. You just sub in x as 15 to find the y coordinate.
That's it. So we get our area equation, whichever version we want. It could be the expanded version we had a little bit earlier, or it could just be this factorized version. Either way, we're going to replace every x with 15. We'll quickly see that's just 15 times 15, which is something. Let me just cheat that out real quick. Squared, 225. Area is 225, and a final check, that was meters squared. That's pretty much, yeah, start to finish, how you do these applications of quadratics. You start by creating your generic area equation From there, you take some steps towards replacing the terms with the ones that you actually want. In this case, we were told the x was the width in the picture, so that's nice and easy. And in this case, we were also told the perimeter, the total amount of wire or fencing we had was 60 meters. That got us our perimeter equation, which we can then use to replace the other variable that we hadn't already gotten rid of. From there, use that equation to draw a quick picture of what you have. Again, using the null factor law pretty much immediately to get your two intercepts, halve it to get your turning point, and then sub in that x value to get the actual y value, which corresponds to area. Cool with that? Anything further to clarify there? Because that's the bread and butter of what you'll do, not only for quadratics, but also for every other type of version that you might come across. This one only has quadratics in it. It is a quadratics chapter, but you'll come across like x cubed, x to the power of 4, mostly x cubed and x squared, but this is the kind of procedure you'll follow every single time. It'll be a matter of create your equation, draw the picture, look at the biggest point, and then sub in. All these are basically the same thing. Let's see if we can do another one with the time we have left. Maybe a slightly different. Nah, the other ones are just... actually, yeah, here we go. So this is the other kind of equation where it was like, you've got fully unknown coefficients in the quadratic, and your goal was to figure out what those coefficients are. We're told a few key features. So point A is 3.1 meters above the door. So for instance, from A to the absolute floor of that blue picture is 3.1. We're told this has a length of 2.5, this has a width of 1.5, and we're going to use all those coefficients to try and get the equation of the parabola. Now that's specifically this thing up the top here on the textbook. It's that part of the picture. We have a bunch of measurements. What could we do? This is CAS as well, by the way. Important to understand that it's also on an XY axis as well. So these numbers will correspond to X and Y values themselves.
You know that the y coordinate of the vertex, which is point A, would be at 0.6.
0.6, possibly. Let me just double check. How did you get 0.6? Yeah.
Because if point A is 3.1 meters above the bottom of the door, and you already have the measurement for 2.5 meters on the side.
Yeah, precisely. So this portion's 2.5, and to make it up to 3.1, you've got a remaining 0.6. So yeah, the y coordinate of the vertex is going to be 0.6. That's its height. That's really good.
And the x, there's only one y-intercept, which is at the origin, and then one x-intercept at the origin, and another x-intercept at 1.50.
Yep, perfect. So you got the point 0, 0 that exists on it. You've got the point 1.5, 0, and you've got almost the full point here. You've got the y value for the a. We just need the x, and that'll be everything. That's all we need.
Well, the y value would just be halving 1.25, so that would be 7 point. So I'm having a blank. 7.25. No, sorry, 0.75.
Yeah, 0.75. There you go. So specifically, that'll be the x coordinate of that a value. Again, as we talked about earlier, it's always the middle of our x-intercepts, the x of the vertex.
Yeah, just be confused, like how, like I understand finding the values, but how do you figure out how to put it back into the generic equation?
Yeah, cool. So let's pop over to the screen share. Oh wait, it was all up here. That's right. So this is our like worst case scenario where you have sort of like 3 random points. we did have a vertex, so we could technically use the turning point form. It wouldn't actually be a bad idea either, but because we have CAS enabled, it doesn't really matter which way we want to go, as long as we have, or let me just get rid of some of these tabs. It doesn't really matter which way we want to go. CAS enabled, you're probably just going to stick with the three-way simultaneous, which is a matter of, because we were told to get it purely in terms of ax squared plus bx plus c, what you essentially do is, on your CAS, you define that function. Does everyone have this CAS? It might look blue as well, but does everyone have the TI Inspire?
Yep.
Yeah, if not, I'll also show the CAS. Yeah, I do have that. But okay, so first things first, we're going to define a function. So that's menu 1 for define. Call it whatever you like, as long as you use proper notation. I'm going to use h of x. And what you're going to do is define that generic quadratic. So a times x squared plus b times x plus c. Make sure you put those multiplication symbols between the x's, otherwise your CAS is going to be, it's going to complain, and it's going to think, hang on a minute, you've called this thing ax, that's not a times x. You do need those multiplication symbols in there. As a side point, if for whatever reason you got any of those letters as bold, so see how this H is bold as compared to this A, which is not bold. If any of those came out as bold, it means you've already defined that letter as something else. Go through and use the delete variable option, which would be simply write the letter and then hit enter. That will then delete it, so you can then use it properly. But okay, we have this. Now comes the easy part, which is going to the simultaneous equation solver. Menu 3 for algebra, 7 for solve system of equations, and then 1 for the solve system of equations once again. We have 3 points, so going to use 3 equations, and we're just going to rewrite these as the A, B, and C that we already wanted them to be. Because we have points, any point can be written as just some basic equation, which is function at the x value of, let's say, 0, which we had, is equal to the y value, which was 0. So this is how you sub in the point 0, 0, right? You've got x0, y0 for that equation. The other thing we had was at x equals 1.5, we also had y equals 0. So we put that one in there. And then lastly, we had 0.75 was going to give us, I think it was 0.6. So h of 0.75 is equal to 0.6. Hit enter, and you'll get all those coefficients. If you're doing it by hand, then it would just look like the math we talked about earlier, which is just doing a simultaneous equation, subbing in those points into the generic ax squared plus bx plus c. In this case, we were told to get a, b, and c, so you would literally write a equals negative 16 on 15, b equals 8 on 5, c equals 0. You wouldn't actually write the rule, you would just give the a, b, and c. Clear enough on how that's worked out? Cool. That brings us perfectly to time, actually, on that one. So we had a look at the 2 main applications of quadratics. One was how you can figure out the generic rule of any quadratic based on the information provided, and the other was how you can find the maximum of a given scenario. Both of those are basically the same thing every single time. You use the information in the question to create a sequence of points, at least in the case of solving the quadratic rule, or you're trying to create your area, volume, whatever equation, and take it from there. Cool. So again, both of these are in the classroom. If anyone has any trouble accessing those, let me know. Yeah, that's pretty much it. If there's any further questions, I'll stick around for a little bit, but otherwise, thanks for coming.
Thanks. I just had a few questions, if you had a few minutes, about the classroom and kind of the structure and curriculum.
Yeah.
Yeah, so I was wondering, so I know that it starts with functions, relations, calculus, probability, and pseudocode. Is that the actual order that the textbook goes through those topics in?
Yeah, yeah. Typically, that's what most classes will do. Most schools will
Yeah.
go through it in that order. Sometimes in year 12, even in year 11, they'll flip probability before calculus. Sometimes.
Yeah. Okay.
Most commonly do your calculus first, though.
Yeah.
They are also, I have gone ahead and labeled what are new to year 12 and what's just year 11. So that'll also help you differentiate between what's actually relevant for any given stage.
Yeah. And when I'm like, say, just studying for methods in my own time, instead of just brute forcing the textbook, should I just, because you have, I can see like under functions and relations, you have like under linear, you have like those like subsections. Should I just go through that kind of content summary documents you have and then head to the textbook? Because I feel like the textbook's a bit long and not fully sure as to exactly how to use it.
Yeah, I mean, one of the disadvantages of the textbook is that it has to give you a bunch of questions. I don't have to do that because the textbook already has it, so I can be a lot more verbose in the explanation. So yeah, I would recommend 100% either read or watch the version. You can see there's like a YouTube link for each accompanying video. Whatever you prefer to have a look at is up to you. It also tells you where in each of the textbooks, whether it's Unit 1, 2, 3, 4, Cambridge, Jacaranda, whatever you've got, it's where you can look at those things. And furthermore, for each of these classes, I actually create a little kind of homework docs. So I'll put that in the chat now. This is the quadratic specific one. It's basically grouped all the specific questions from those chapters into similarities. So I kind of talked about it a bit earlier, which was all these equations kind of look the same. So question 1 is basically the same thing as question 2. Same thing as question 4. You'll see in that document, those are all bundled in the same group of questions. So it can help you be a bit more efficient that way as well by saying, hey, if you want to practice this kind of question, have a look at this section.
Yeah. So for my independent study, I can just kind of click onto the classroom subtabs, just keep working through everything.
Yeah, precisely.
Yeah, I just think it's really helpful because it has everything kind of listed out. Because with the textbook, it just was a bit daunting to just have
sure
one,
does.
especially with the 3-4 textbook. It's like 1,000 something pages.
1,000, is it? Holy shit. Nice. Yeah, I mean, it is a big slab of text, so yeah, I do like the structure of being like nice and modular. No videos longer than like 15 minutes, and you can watch it 2x speed if you need to speed through it. And it's all sectioned out in like the key examples rather than trying to bog too. I feel like the textbook sort of bogged down too much in like the theory of everything, which is nice, but you kind of want to know the application of the theory and the layman's terms of it. But yeah, they are written to make things faster than the textbook. Yes.
Yeah.
Cool.
Awesome. Thank you.
No worries. I'll leave you to it.
Bye.
Take care. Hey, you got something for me? Oh, never mind.